Connecting to the cosmos, exploring NASA's space internet.
Hey everyone, today we're diving into NASA's incredible communication system that allows us to connect with spacecraft across the solar system. We're talking about the Near Space Network and the Deep Space Network, so let's get right into it.
Whether it's missions exploring Mars, satellites orbiting Earth, or the Voyager spacecraft traveling beyond our solar system, these two networks keep NASA connected to it all. But what's the difference between the Near Space Network and the Deep Space Network? Let's break it down. What is the Near Space Network? Just like the name suggests, this network supports communication with spacecraft in low Earth orbit or geosynchronous orbit. Think satellites that are well near to us, such as weather monitoring, GPS, or even the International Space Station.
NASA's Near Space Network combines ground stations and space-based relay satellites to maintain constant communications with these missions. Ground stations, like those in White Sands, New Mexico, and Guam, communicate with satellites and spacecrafts close to Earth. One of the key components of the Near Space Network is the Tracking and Data Relay Satellite System. These satellites act as intermediaries, allowing for near continuous communication with missions that can't always have a direct line of sight with Earth. These satellites orbit high above Earth, relaying data between the spacecraft and the ground stations.
The NSN helps ensure that Earth observation missions have a steady stream of data to and from Earth. Without this network, we'd have a lot of gaps in our ability to track and communicate with satellite. What is the Deep Space Network?
Unlike the NSN, which focuses on communications that are close to Earth, the DSN was designed to communicate with spacecraft that have left Earth orbit. These missions are exploring other planets, moons, asteroids, and even the far stretches of our solar system. The DSN is one of the most crucial parts of deep space exploration. Its ground stations are strategically located in California, Spain, and Australia. These locations are spaced roughly 120 degrees apart, so that NASA can maintain constant contact with spacecraft no matter how far they travel. The DSN's massive antennas are capable of receiving weak signals from spacecrafts that are millions or even billion miles away.
Like how we re-established communication with Voyager 1 earlier this month. The DSN complex have different size antennas, including a 70 meter, 34 meter, and 26 meter antennas. For example, DSN complex uses the 34 meter to talk to Webb, with the 70 meter antennas as backups. The DSN is how we receive images from the Mars rovers and Webb, data from the Voyager spacecraft, and even mission critical information from landers on distant worlds. DSN supports different radio frequencies, such as the S-band and the Ka band frequencies that Webb uses. S-band has a lower bandwidth, and that is used to send commands to the spacecraft to monitor the health and safety of the observatory and for ranging. Ranging is the process of determining Webb's position and trajectory by the delay between when the signal is sent up and when it is received back on the ground. The Ka band is used to download data from the spacecraft. If we use the S-band to download data, it will take many days. With the Ka band, it takes much less time, and the data is usually downloaded within a couple hours. Each mesmerizing Webb image that has graced our screens would not have been possible without the support of the DSN antennas. Sandy Kwan. How the NSN and DSN work together.
While the NSN and DSN handle different missions, they both play crucial roles in space exploration. For example, NASA's Artemis mission to the Moon will rely on both networks for communication. In low Earth orbit, the NSN will handle the connection, but as the spacecraft travels deeper into space, the DSN will take over.
This handoff between networks allows NASA to maintain constant communication with missions, whether they are close to Earth or traveling beyond the Moon. Challenges of space communication.
One of the challenges with the Deep Space Network is dealing with the time delay in space communication. For deep space missions like the Perseverance rover on Mars, it can take anywhere between 5 to 20 minutes for signals to travel between Earth and Mars, and this delay has to be accounted for when sending commands or receiving data. On the other hand, the NSN doesn't experience the same long delays because it deals with spacecrafts and satellites that are much closer to Earth. This means near real-time communications for things like monitoring weather patterns, GPS navigation, and streaming data to the ISS.
Why the NSN and DSN matter.
Whether it's the International Space Station orbiting just 250 miles above us, or Europa Clipper, or the Voyager spacecraft over 14 billion miles away, the Near Space Network and the Deep Space Network keep NASA connected to its spacecraft. Without these networks, we wouldn't be able to monitor our planet, explore other worlds, or unlock the secrets of the universe. So next time you see a stunning image of space, check the weather on your phone, or use GPS, you'll know that NASA's network played a huge role in making that happen.
Future developments.
As NASA and other space agencies are planning missions to the Moon, Mars, and beyond, both networks are evolving. The DSN is expanding with new technologies like laser communications.
This technology promises transfer speeds of up to 100 times faster than traditional radio waves, enabling us to send and receive more data than ever before. Such as NASA's Laser Communications Relay Demonstration, which launched in 2021, which is a key project designed to refine this technology for two-way, high-speed laser communications. Another project, Terabyte Infrared Delivery, set records with its 200 gigabytes per second data rate, paving the way for streaming high-quality video and complex scientific data from space.
NASA also has upcoming missions that will put laser communications to the test. The Luma-T mission on the ISS will use lasers to create a high-speed link between the ISS and the ground station. And with the upcoming Orion Artemis II mission, NASA aims to utilize laser communications for sending vast amounts of data from lunar orbit to Earth, paving the way for real-time updates for future moon missions. Meanwhile, the NSN is getting ready to support a whole new generation of missions, including commercial spacecraft and more Earth observation satellites. These advancements will help handle the growing demand for data as space exploration becomes more ambitious. The future for space exploration is bright, literally. Laser communications are going to make NASA missions faster, more efficient, and more engaging than ever before.
And they continue to evolve and adapt to meet the demands of more ambitious missions, from returning samples from Mars to exploring the icy moons of Jupiter.
So there you have it, the Near Space Network and the Deep Space Network. These networks keep us connected to our machines exploring the unknown. Thanks for watching, and as always, keep looking up.